Hello, and welcome to What is Dependency Injection? My name is David Donahue, and I'm going to walk through some concepts and definitions and ultimately some examples of what dependency injection is and how it's implemented. Now you might be wondering, what is dependency injection at all? Maybe it's this buzzword that you've heard a few times, but you've never used it in your career and you don't see why you would want to. Or maybe there's someone on your team who's insisting that you use it, or someone who's implemented it and you have to support that code. And you're wondering, it looks so complex, it looks like it's just another layer of indirection that's entirely unnecessary. So again, why would I need it? And so to address that, we're going to walk through the definition of it, what dependency injection really is at its simplest, why on earth we would use it. That is, if it's making the code more complex, then why is it a good idea? How does it actually make things simpler if it looks more complex? And finally, we'll look through some examples in Visual Studio of an application which evolves into a dependency injection-enabled system. So let's start with the first point. What is dependency injection? At its simplest, it's an implementation of the dependency inversion principle. This is one of Robert Martin's 5 solid principles of object-oriented design, and it basically requires that any dependency an object has should be provided to that dependency instead of internally created within that object. It essentially states that abstractions should not depend on details. Details, instead, should depend on abstractions. What this means is that if you have one object which depends on another object, it should really depend on an abstraction of that other object and allow that other object to be provided to it, rather than have a direct dependency resulting in tight coupling. This is often summarized as require, don't instantiate. And at its simplest, that's essentially what we're talking about. We would say that if object A needs an instance of object B in order to do its work, then object A shouldn't internally create a new object B. It should require that someone provide it with an instance of object B. So let's look at a simple example of that. We have this widget object, and it has this widget dependency, which as you can see is an interface. And it needs that dependency at the bottom in the doSomething method to do something. But instead of creating a new widget dependency object, you'll see that its only public constructor requires that someone provide it with a widget dependency object. So the widget object can do its thing as long as someone provides it with whatever dependency it needs. This could even be made simpler. If there's only one method on the widget object which needs that dependency, that method could just expose that dependency as an argument to the method. And this isn't using any sort of high-level patterns or practices. This isn't using any frameworks or architectural designs. But what this is doing is inverting that dependency. It's following the principle to the letter, basically saying that in order for this object to do what it needs to do, it has to be provided with that dependency. So you might be wondering, what difference does this make? Why on earth would I want to use this? If it's just that other layer of indirection, how does it improve anything? Well, the first answer that's often given is unit testing. We can unit test things very easily if we can replace our dependencies with mocks or with different implementations. For example, we might mock our data access layer so that we don't require an instance of a database to run our unit tests. We could mock it with a mocking framework, or we could mock it with perhaps a fake data access layer, an in-memory implementation of a repository, which is just a list of instances rather than an actual database. We could mock the file system so that we don't need to actually write to a file system in order to run our tests. We could just assume that the file system worked, and that way our tests are really testing the business logic and not the file system itself. We could mock an email server, for example, so that we're not actually sending out emails. We don't have to make sure that the system is configured during testing to send to an empty test account rather than to actual customers. Instead, we just don't use the email server at all during testing and use a mock implementation instead. And the dependency inversion allows us to use the same code, swapping out these implementations. Other possible uses for this are a more modular design in the application. For example, as I said earlier, we might have multiple different implementations of something. Let's say we have a dependency on an external web service, some third-party provider that gives us some service. Maybe, for example, post office lookups. And so we use this third-party provider and we require it as a dependency in some of our business logic. But then let's say we sign a contract with another provider. They give us the same service but for better rates. And so we want to change that implementation. Well, if we were tightly coupled to that implementation, then we would have to be very careful to make that change. And it's sort of an all or nothing change on that one production release, probably on a weekend at some point. But if we're not tightly coupled to it, what we can do is create that other implementation, swap it out for testing, and swap it back without ever changing anything in the production system or without any changing any of the business logic, because that business logic doesn't depend on the implementation, just on the abstraction. We might have more configurable applications where we have multiple implementations of various things, and different applications throughout the enterprise would use different implementations of it. Well, using something like a dependency injection framework or even something entirely homegrown, we can make that all configuration driven so that any given application can pick and choose which dependency it wants to use. This helps us upgrade our infrastructure more. An example I gave earlier was for switching to a new provider of a third-party service, or maybe we want to switch to a new data access layer. If, for example, we've been using Link to SQL for our code for a long time, and we want to upgrade to something like Entity Framework because Link to SQL is pretty outdated and we don't want to use it anymore. We don't want to depend on it. Well, if everything throughout the entire code base is tightly coupled to that Link to SQL implementation rather than an abstraction sitting over it, then we would have to change everything throughout the code base. And that's a very significant change and requires a lot of testing. If, on the other hand, we only have to depend on that abstraction and we can be provided with an implementation of it in our code, then we don't have to change any of the business logic. We don't have to change any of the other assemblies, any of the other projects. We only have to create a new implementation, and once it's ready, once it passes all of the tests, we can swap it out immediately. This also leads us to a very clean separation of the concerns throughout our code base. It helps us maintain the single responsibility principle, and this allows us to ensure that any given implementation is only responsible to the application that uses it, or the handful of applications that use it. It increases code reuse, because as long as these abstractions are well defined to what it is that they're supposed to provide, any implementation that satisfies that abstraction, or any implementation that basically satisfies the interface that uses it, can be reused in any application or any project that needs to use an instance of that interface. This helps us with cleaner modeling, because we can, by pushing out these abstractions, really identify what is the business logic and what is infrastructure logic. There's a lot of examples in all sorts of business domains where we might have a business object which has all of this internal code for dealing with the infrastructure. Maybe it's data access code, maybe it's code for hitting a web service, or code for doing anything that's in the infrastructure. Now, none of that infrastructure is really business logic, and so it doesn't really belong in that model. The model is really there to implement the business rules, and all of that infrastructure and architecture concern, those belong to the architecture team. Those belong to the developers. They don't belong to the business. And this goes back to that single responsibility principle again, where you would have that one object which is responsible to its business owner, and another entirely separate object which is responsible to the software architect. So then how does all of this simplify code? Well, let's take a look at an example. So we have this computer object, and it has this power supply, of course, and in order to power on the computer, it has to power on the power supply. Now you see what we're doing here is we're creating a new power supply inside of the computer. We're setting it to a 400 watt power supply. It's not a very beefy computer. And then we power it on. And this works. This is very simple, very easy to understand. But the problem is we're tightly coupled to that one power supply. Instead, let's take a look at this inverted dependency where we're provided with a power supply. We still power on with it. We still have that power supply implementation internally, well, not the implementation, the abstraction internal to the computer object, but now the computer requires that it be provided with a power supply. Now there's a couple benefits here. If we go back to tight coupling versus loose coupling, in the previous code, if we wanted to use a different power supply, we would have to change the computer object. Now, I understand this is a contrived example, but suppose this was a larger model on a larger business system, and if we made changes to this model, that would require retesting it. That would require notifying whatever business users are responsible for this model, any users who depend on it, anybody who owns it, essentially anybody to whom this is responsible. And they might want to know why we're changing their object when we were supposed to be changing our object, which in this case was the power supply. In this case, we have this 400 watt string hard-coded. If we only wanted to upgrade to a 500 watt power supply, we shouldn't have to change the computer. We should just put in a new power supply. And with this implementation, we can do that precisely. In fact, if you think back to the clean modeling concept, think about the real-world objects that we're modeling here. If you wanted to upgrade the power supply on your computer, you would just provide the computer with a new power supply. You wouldn't change the computer at all. Now we might also use something like this. This is setter injection, where the power supply is simply a property of the computer, and anytime you want to use a computer, you have to provide that property with a power supply. Now, this is of course again a contrived example. We would want to put in some sort of error checking here, of course, but it's just another way that we can invert that dependency by providing this externally visible property that we can set with the object that we need. Another pattern, one that I commonly use, the service locator pattern, is where the computer internally requires that power supply, but rather than require that consuming code provide it with the power supply, it calls another object in the domain to go out and find one for it. Now, for the real-world objects that we're modeling here, this might not make the most sense. I just want it to be consistent with the contrived example. But essentially, this takes the responsibility of connecting an interface with an implementation, and it puts that into that one place. We see this IOC object, this inversion of control object. And this is a pattern we often see in dependency injection frameworks. So finally, let's take a look at some examples of what this really means and how we would implement this. Now there are lots of different frameworks that are used for dependency injection. This is a very small subset of them. These are probably some of the more popular ones. There are some that are even as simple as a single class that you add to your solution, something that doesn't really require its own large framework. There are some that are very big and very feature-rich, others that are geared more towards speed and simplicity. You can pick and choose or even write one yourself. There are lots of examples online of how to write a simple dependency injection container in sometimes as little as an hour or sometimes as little as 30 lines of code. So we'll look at some of this code in Visual Studio. The first thing we're going to look at is this project disamples.nolayers. And as you can see, there are no layers in this project. It's just a simple web application. It has a controller. We have this product controller, which creates an AdventureWorks database context and uses it. Gives us a list of products or a single product, or it might update a product. And how this runs is very simple. Or at least it should be. Alright, here we go. So let's go to products. We have our product list. You can go to any page and edit a value. So that's all well and good. And it's very simple. And in fact, we can chart that out here. No layers. It's just a web application that directly hits a database. And for very simple applications, that might be fine. In a larger system, in anything more, well, to use the term enterprisey, it's sort of design 101 that you would have a data access layer instead of directly accessing the database. Something where there would be an assembly in between your application and your database. And so let's take a look at that. So here we have our application assembly, and we have our data access layer. In this case, the data access layer exposes a repository for the products. We can get all the products, or we can save a product. And then the controller does pretty much what it did before. Creates a repository this time instead of the database directly, or the data context rather. But the rest of the code is pretty much the same. We get all of them, or we get one, or we save one. And the behavior of the system is also the same. And again, we can just set a value. It's all very simple. And so this is probably what most of us are accustomed to seeing. It also has that tight coupling. If we wanted to change our data access layer, if we wanted to go, let's say, with, again, Entity Framework, because this is just using link to SQL, then we would need to change our application as well. So the pattern that we want to go with is something more like this. Now, as you can see here, we have these interfaces, and everything points toward the interfaces. The interfaces themselves don't depend on anything else. Now, the web application also has this other coupling to the data access implementations, and those implementations are what couples to the database. Now, that other coupling we want to pull out, but we'll get to that in a minute. First, let's look at what this code really looks like. This uses dependency injection, and so we've added this abstract data access layer system here. What this does is give us our persistence ignorant model, which is currently just a simple DTO, and our interface for the repository. And then our implementation just points back to that repository, and it's an implementation just like the other ones, a simple link to SQL code. And if we look at the references, we'll see that it just references that abstraction. The abstraction doesn't reference anything. And now the application references the abstraction, and for now the implementation as well. Then if we look at the controller, again, it does the exact same thing in all of the actions. But you see here that we're using this constructor injection here. We have our interface for the product repository, and we require that we be provided with an implementation of that interface, and then we use that implementation throughout the other actions. Now, to do this, we needed to use some sort of dependency injector. In this case, we're going with my personal framework of choice for no other reason than because I have most experience with it, and that is structure map. And so in an ASP.NET MVC application, we would have this thing called a dependency resolver. And this dependency resolver allows us to use constructor injection on our controllers. Now, of course, this needs to be configured. And so the first thing we do when the application starts up, after we do all the regular application stuff, is initialize that container, that dependency injection container. And so we use some structure map code here to configure it. This basically says, for that product repository interface, use the product repository implementation. And then, of course, we call this MVC object, this dependency resolver, to set the resolver to this other object we have here, which is our structure map implementation for dependency injection. This is really just a pass-through. This implements an MVC interface called iDependency resolver, and essentially it exposes these two methods, getService and getServices, which for any given type just return an instance of that type. And again, this is just a pass-through object to a structure map container, a dependency injection container, which exposes very similar methods for getInstance or try to get the instance or get all instances. There's essentially a one-to-one relationship here between what MVC is using to resolve its dependencies and what structure map, or just about any dependency injection container or framework, is going to use to resolve dependencies. And so if we look back at the configuration for it, oops, where was that? There it is. We see that we used this line of code to define for one interface, provide this one implementation. Now I'd like to point out that this is the simplest possible configuration we could do for this. Now if we have hundreds of interfaces and maybe thousands of implementations in this very large domain where we can swap out all of these different implementations for lots of different reasons, you can imagine that this would get pretty complex. And so just about any dependency injection framework will have configuration options for it that would allow you to define patterns for this. For example, there's a built-in configuration pattern in structure map, which basically says for any object I find that, or for any abstraction I find that begins with I something, look for a class that matches the name without the I and provide that. There's lots of different configurations you could use. You could see the pattern I usually stick with here is to append the word implementation for the concrete implementation. This is primarily because I don't like to decorate my abstractions with the I moniker, because the abstractions are really the names of these concepts throughout the domain, and I don't want to decorate my business concepts with infrastructure concerns. But that's another argument for another time. Any pattern that you use, any convention that you use, you can favor that convention over direct configuration. But essentially, this project does the same thing that the previous projects did. All it does is use a dependency injection framework to provide the controller with that data access layer implementation. And so this allows us to create new implementations without having to change the controller or minimally changing the application. And we'll address that minimal change shortly. As you can see, the behavior is the same. Now that minimal change is what I was referring to with that lighter gray arrow, where the web application is still dependent upon the implementations. And in fact, if we had a large team of developers who are being pulled in lots of different directions and have lots of different deadlines and priorities, some undesirable changes might slip through the cracks here. Instead of using this injected implementation that depends only on the abstraction, the developer might do this. As you can see, we can go directly into this product repository implementation and get those. Or even a step further, we might create the data context, return products, and select a new product. And that's not something we want to do, because this is now returning us to that tight coupling. That developer who was in a hurry accidentally leaked these abstractions, leaked these dependencies into the application, and put us back into a tight coupling situation. And so, how do we address that? How do we get rid of that light gray arrow? This is where we go to a slightly larger pattern here. And this is something where I very often use the service locator pattern that we talked about earlier. Now here again, the interfaces being the core of the domain, where we would have our business models and our various business concepts, everything points inward toward that. It's critical that no arrows point outward from that to something else, because that would introduce a dependency from within those business logic objects. And now here, the web application, or any application in the domain, instead of pointing to all of the implementations we might have, for example, a data access implementation, a third-party service implementation, any sort of infrastructure concerns like logging or file system, anything like that, it would only point to this one dependency injection implementation and essentially take all of those couplings and put them in a single coupling, in a single place to change. So let's look at what that does. So now we have this domain project, which again has our persistence ignorant model, which again for now is just a bare DTO. And it has our product repository interface again. And we could have other interfaces for any of those other concerns we talked about. And it has this other interface here, this IOC container. And this is what I'm going to use for that service locator pattern. And you'll see this get instance, somewhat similar to, in our previous example, the dependency resolver from MVC, which gets a service or a list of services. And additionally, we have this static factory, which has this current instance of that container. Now, this is going to need to be initialized, just like anything else, because as you see in the application, in our controller, we call that factory and tell it to give us an instance of that interface, and then we use that instance just like we used it before. And so, just as before, we're going to initialize this. So we initialize it when the application starts up. This time we're calling this other object, this initializer, which I have in our separate assembly for defining the dependency injection. That initializer does the same thing. It configures our one single dependency in this case, and then it sets that factory to an implementation which uses this structure map version. And so what this means is that as a dependency, we've also abstracted structure map. Now the application doesn't need a reference to structure map, which it did in the previous example. And so this also allows us to even switch out our dependency injection implementation itself as being its own dependency. And we see also that this references the domain, and it references the implementation for that domain interface. And that implementation is, again, just a simple link to SQL implementation. I've pulled out some other methods this time, but it's about as simple as any repository implementation will get. And so looking through these references again here, we see that the implementation references the domain, the application references the domain and the dependency injector, and of course the domain core doesn't reference anything. And so when we go back to the controller, we can run this application and see that the behavior is again the same as it's been the whole time. All we've really been doing is pulling out these dependencies into these separate concerns, these separate projects, which can be reused throughout the domain or easily replaced or easily mocked and tested in isolation from one another. The behavior hasn't changed. And so there are a few additional benefits that we might see as we look through something like this. For example, if we look back to our initial layers concept, one thing we were talking about here was that if we wanted to change the data access layer, we would have to change the application to go with it. We would have to change these references. We would have to change the controllers. If our model is different from the data access layer, we would also have to change our views. For example, let's look at our product view. The model for this comes from the data access layer. And so if we went from a link to SQL implementation to an entity framework implementation, we would have to change this view. And now any book on software development or object-oriented design is going to tell you that if you have to change your user interface in order to accommodate a database change, that's a very tightly coupled system. And so we wanted to move away from that. So now in this domain, if we wanted to change that data access layer, excuse me while I collapse these, we could just create another implementation here, side by side with this one. Our dependency injection implementation would add a reference to that second one, and anytime we want to use that second one, we would just change our configuration, which here is hard-coded, but this could be config-driven, it could be convention-driven. We could even have named instances. I think one of the overloads for this, no, it's not for this one, so I could look at that another time. But we could have named instances where we say, whenever I get an implementation of this, it would be provided with some sort of key so that if I have multiple implementations, it can specify which one it wants. Some frameworks don't do that, some do. It just depends on what you really need to use. But the point is that these two implementations can sit side by side, and the application, and more importantly this shared business logic domain across many applications, will never see or know that there's a difference. Now this can help with something else in larger enterprises as well. We talked earlier about a single developer who was under different priorities, different restrictions, or maybe didn't understand the pattern immediately and sort of bypassed the dependency injector, and we wouldn't want that. Well, here we can't do that. If we tried to directly call the data access layer, we don't have access to the data access layer. we only point at the dependency injector implementation. We don't point at the data access implementation. And so in order to do that, that developer would have to change the references in the project, which is a bigger change. That might be a clue to the developer that, hey, there are other things in this application which use the database, so clearly there must be a way to use the database without having to change these references. Or, more to the point, we might use this to try to automate some of our code review statistics. As we know, code reviews are generally a good thing to have on a large team, even a small team, any team where there's multiple people. But we can't mutually review every line of code that's written. So we'd want to identify changes as high risk or low risk in some automated triage so that we can review the ones that are high risk. Well, if we look back at our layers, if we wanted to change anything anywhere along this, we'd probably change a lot of this. Stuff in this would change, and stuff in this would change for just about anything that we do. But here, we can separate out those changes for high risk and low risk. If something in an application changes, that's pretty low risk. It will only affect that one application, and it will probably, if it causes an error, would probably be caught by QA or UAT testing. If something changes in an implementation, again, we'll call that medium risk, or maybe a low to medium. Again, if there's a problem that it introduces, then since this is a component that exists in isolation, we should have some automated testing against this component. And so any problems that are introduced should be caught by the automated testing. Now we might want to review this change if we have time, because if it's something that's not caught by testing, but would be caught by QA or UAT as a problem that was introduced somewhere else, a regression error, then that would mean that a change to one thing affected something it shouldn't have. This could be that there's a subtle violation of the single responsibility principle somewhere in this code, and we could use that as an opportunity to refactor that a little bit. So again, we'll call that medium. If something changes in the domain, that's the business logic. We can call that medium again. It's shared across the whole system, but because it's the business logic, we have unit tests that are against it, or at least we certainly should. And again, it's something that should be caught by QA or UAT in this case, because this is the logic of the system itself. So we would want to review those changes, but they're not really high risk. If something changes in this project, that would be pretty high risk, because the architect would want to immediately review that, because the architect is the responsibility for this project. In the single responsibility principle, this entire project is responsible to the architect and only the architect. There's no business logic here. There's nothing that's going to be manually tested here. And so the architect would want to review those changes. And again, if we look through any of these and find that the references changed in any project anywhere in the system, we could also flag that as high risk for the architect to review, because that could mean that someone added a reference that they shouldn't have added to try to bypass the dependency injector. And this triage can be automated in our continuous integration build process, so that the build system looks for changes in these specific areas and flags them and produces a report on low to medium to high risk changes. But this is just sort of one idea among many of things we can do from implementing dependency injection. As we see, these patterns that evolved from no layers to what most of us are accustomed to is simple layered application, and for most simple applications this makes a lot of sense and does the job just fine. As the enterprise grows and the business domain grows, we might want to start to introduce dependency injection so that we can alleviate some of the coupling, alleviate some of the maintenance of these larger systems, and over time grow into this overall domain infrastructure that allows us to have our applications use that one dependency injector which maintains all of those implementations against the abstracted interfaces in the domain. That's pretty much it for dependency injection. If you have any questions, feel free to contact me online. And thank you for watching.